Okay, so example 10 here, this is another rate in, rate out problem similar to that breakfast line problem that we had on another homework. Alright, so it says a new Broadway show is opening and people are calling in for tickets. We have an initial amount of people that have called in. So it says there are 300 people waiting on hold on the phone when the operators start processing calls. This is an initial amount or initial condition. I'm going to go and write initial condition. Rate in, rate out problems often have some type of starting amount that we have to take in consideration as well. Alright, and then it says they can handle 400 calls per hour. This is going to be my rate out because this is people getting processed, so no longer on hold. And notice it's that constant rate of 400 calls per hour. So no matter what hour, during that hour, 400 calls will be processed. And then it says the graph at the right, but really the graph below consists of 4 straight lines and shows the rate at which new calls are coming in. So this graph here is COT. This is my rate in. This is people being added to the list of those on hold. So we have people that were already on hold, people adding onto it, and people that are getting processed. So it's taking into consideration all these pieces. Now remember, our rate here is in calls per hour. And we can see that our rate of people calling in is changing over time. But again, our rate of people being processed is the same 400 no matter what time. Now, if I were to integrate this rate here, because this is rate in calls per hour, if I were to integrate this rate, what would that give me? Remember, integrating takes you back. So we had calls per hour. What would integrating take me to? Yeah, how many people have called in? So just the number of calls. Remember, we can look at our units and kind of just drop one of our times, if you would, or multiply that together. But if I have a rate going back, integrating takes you back to that version. Okay. Part A says how many people have called in by the end of the 6-hour period. So we have to consider that as soon as they start processing calls, we already have 300 people waiting on hold, right? And then to figure out how many have called in, so at time 0, we already have 300 on hold. Then to figure out how many have called in between 0 and 6, we need to integrate that rate. Because integrating that rate, again, gives me the number of calls that have occurred between 0 and 6. But they did not give me a function for this. So what do I have to do in order to evaluate that interval? Find the area. So and the integral is just the area underneath the curve. Here we don't have a function, so we're going to actually just find the area here. Now you could have broken this up in different pieces. You might have done, I wouldn't recommend a trapezoid there because it doesn't go all the way over. But you might have done a series of trapezoids or triangles. Let's see. Let me see which one we keep at. I did mine slightly differently, but you should arrive at the same conclusion. So this was 600. This rectangle ended up being 700. And if you take this big looking triangle, 600. And then we have 200 and 100. Now the thing with AP is that graders are not, the AP readers are not allowed to consider your work on the graph. They can only consider your work in the workspace. So we need to actually list out these values in place of this integral here. So we have 300 plus, and then I'm going to list out these different ones. If you use different values, that's fine. Make sure you list those out. So we have 600 plus 700 plus 600 plus 200 plus 100. And what are we talking about again? 9 people. Yeah, 9 people. So this many people. And again, since this is for response, we can just stop right there. That is our answer. Now, this could be a 1-point problem. It could be a 2-point problem. Sometimes they might break up the points where it's 1 for your work, 1 for your answer. Sometimes both points are just on your answer. And again, I don't recommend that we simplify because sometimes we simplify wrong. All right, questions on part A. Okay. Now B says it's the number of people who are waiting on hold increasing, decreasing, or staying the same between hours 1 and 2? And justify your answer. This is a lot easier than some people make it out to be. It's pretty simple. So we need to know if the people who are on hold is getting bigger or if it's getting smaller. So if we consider how many people are on hold, so we're looking at hours 1 and 2. If we consider how many people are on hold and also how many people are being processed, whichever value is larger will help us know if more people are being stuck on hold or if they're getting processed faster. All right. So our rate between hour 1 and 2. So the number of people who are waiting on hold. What is my rate? Let's just break it up between rate in versus rate out. How many people, or what is my rate of people being put on hold between 1 and 2? The rate of people calling in between 1 and 2. 700. Now, did that 700, somebody say, calls per hour? Now, did that 700, did that come from my amount I found under the curve? Did it come from this piece? Or did it come from the height of my curve? Good, the height, because the curve itself tells me my rate in. So the height of the curve lets me know between hours 1 and 2, I can see 700 people are calling in, or at a rate of 700 calls during that time. Okay, now if we consider our rate out, how do I know what my rate out is? It's just that 400 calls per hour. So I have 400 calls per hour getting taken care of. Alright, so here I can see I have more people calling in than is being processed. So does that mean that I have people wait on hold increasing, decreasing? Yeah, we have more people coming in than going out. Alright, so then we can go ahead and say then that we know it is increasing. So the number, let's go to the answer next. The number of people, remember no abbreviations, as painful as it may be, the number of people waiting on hold is increasing. And increasing when? They asked us specifically between hour 1 and 2. Increasing between hour 1 and hour 2. Since the rate of people calling in per hour is bigger than the rate of people being processed per hour. There's, you have a little more. Okay. Questions with that one? Do make sure you actually answer the question. Don't just do this and stop and think you're done. You've got action numbers first. All right, now C. Leave it to AP to always throw the letter K into some for your response. And it almost always ends up in the last portion of our response. So it says, write but do not solve an equation involving an integral expression or expressions of C of t, whose solution gives the earliest time K when there's no one waiting on hold. Okay, so earliest time K. So instead of our variable, or our bounds, if you would, our time being t, we can actually put K for it, where there's no one waiting on hold. What does that mean for us in the context of this problem if no one is waiting on hold? How can we know that to be true? When would that occur?
When the rate out is greater than the rate in.
Yeah, would you agree? Even if just once they're equal, then there's going to be no one on hold, right? So yeah, if we have more people being processed and coming in, for sure there's no one on hold, but as soon as that happens is when they're both the same, right? So if my rate of people coming in, or the total amount of people coming in, is equal to the amount of people being taken care of, and that means there's no one left to be on hold. They've all been taken care of. So let's think about those number of people coming in. So we have, again, that initial amount that have to be taken care of. because starting right away at time 0, we have 300 people that have to be processed. It's going to take a little while to do that. But then on top of there, we also have the amount of people calling in once calls start getting processed. So starting at time 0 to some unknown value k, and we're trying to find that k at which we finally do have the missing of my calls coming in. Okay, so this here is going to be the number of calls coming in. Right? We have our initial amount plus this integral will give us how many have happened up until that unknown k value. Now we compare that with the number of calls getting processed. And there's a couple of ways that you could do this. Remember, we have a constant rate of 400 calls per hour. So you could represent this as integrating the constant value 400 dt from 0 to k. Because again, starting at time 0, they can process the calls, and we'll be processing it all the way up until time k. It's that constant rate of 400. Or you could just do it this way. 400k, because again, k represents the number of hours that we're at, and it's 400 per hour. Does that make sense how either of those will give us the same thing? Questions on that? Okay. So this here represents the number of calls out, if you would, or being processed. Okay. So again, we said that once these are equal, then we know that there's no one waiting on hold. Now, you could also do this a different way. I think the answer key said the 300 plus this integral minus the 400k equals 0, right? If they're equal, then subtracting them equals 0. That would be fine as well. Either way would be okay. And again, notice it says do not solve. So you stop. This here is your answer. A lot of times when they throw k in with some type of integration problem, k ends up being one of your bounds. Not always, but a lot of times. Questions on that? Yeah, on the key it says, I think 300 plus the integral from 0 to k is ct dt minus the integral 400 dt equals 0. Same thing, either way would be. Alright, other questions with this plugin?
Oh, I just had a question about examples.
That's fine. Before we go there, do we have any questions on this particularly? Okay. Let's go ahead and go back to 6 then, you said.
Like, I got how you found the area and everything, but I didn't understand how you figured out, like, the base. Like, I got how you found, like, the radius of the circle, but how you found the base of the circle and the
Base of the triangle.
triangle, yeah.
Good question. So good job recognizing this is half the circle. So how do you know what your radius, how did you know your radius of the circle?
Because it goes up to 3.
Okay. So it has this height of 3, so that means my radius is 3. Well, what do we know about the radius anywhere in a circle? Always the same, right? So isn't this a radius? And then this is also radius. So what we have is right here is 3, plus another 3 means that right here is 6. Does that make sense? Mm-hmm. So we have a diameter of 6, if you want. That's a good question. Other questions on this one? And we did quite a bit in class. Good, Nick? Okay, so questions on our homework. Alright, so let's take a look at that other one, the 3-2A. Alright, I want to take a look at a couple specific ones on here. Let's start off with their absolute values, the 21 through 24. And then we'll take a look at our transformations, the 28. Alright, so 21 through 24. These are really good AP style questions. You've got to be very careful about where your absolute value falls. 21, you have to first integrate. So find that total area under the curve, considering both positives and negatives. Remember, positive is above the x-axis, negative is below. Then once you have added all those areas together, then you take the absolute value of it. So for example, it says from negative 2 to 1. So from negative 2 to 1. So I would go ahead and find these areas. My computer's making noises. What do we get for this area here? 2, 4, negative 4?
Yes.
Raise your hand if you got negative 4. Okay, that's good enough. Okay, so negative because it's underneath, right? So do your area like normal. This is area equals 1/2. My base is 2. My height is 1, 2, 3, 4. Then once you simplify that, then tack on your sign, whether it's positive or negative. All right, what do we get for our area over here? 2. And positive 2 because it's above. So for this particular absolute value, we want to first take that integral. So first find that area. So negative 4 plus 2 gives me a negative 2 area under the curve. Then do the absolute value. So first evaluate the integral. So all the area underneath, add it together. Then do the absolute value. So you should have gotten 2 for that. Now this is different from number 22. So number 22, you are first doing the absolute value of the function. And what does the absolute value do? Makes everything positive. Good. So any negative y values, it turns it into a positive. So here with 22, we want to first take the absolute value of any of our values that we have, then integrate, find the area. So essentially what that does, we're going from negative 2 to 1. Oh, not too bad. We already have those areas. How can we begin? All right, so again, absolute value of our function means anything that was below gets put above. So if we think of our absolute value here, then this line, these are all negative y values, become those positive y values. So this is 1, 2, 3, 4. So it's really 1, 2, 3, 4. So we have then that this piece is the absolute value of my function from negative 2 to 1. So we're finding these areas. So what that did is that takes my negative area now turns into a positive. So I now have only positive areas to add together. So really all it does is it just makes me a negative area, it makes it positive. But you make those areas positive before you add them together. So then I have 4 plus 2. Which would give me an area of 6. Questions with that?
How do you know when you're creating the curve is negative and positive?
Great question. So if, looking at my graph, basically if it's above the x-axis, positive. So this is a positive area. This is all positive area. If it's below my x-axis, negative. So this whole thing is a negative area and a negative area when we're looking just at our graph. Now, the only thing you have to be careful with is that, let's see if they did it to us.
So just put it as
There's
negative.
one of our
So within the absolute value, it's
that's
negative.
going backwards.
Yes, so backwards is where it's going to change it. So I think 13 messes with us. So 13 says from 0 to negative 3, we always want to go from the smallest bound to the highest bound. So this is where we want to apply that product that we can switch the bounds. So I want my lowest to highest. But what do I have to do when I switch my bounds? Okay, negate the whole integral there. So then for here, when I go and do my integral from negative 3 to 0, this is going to be a negative area, right? I think it ended up being negative 6, if I recall correctly. So then this, I'll just go over here. the integral itself, from -3 to 0, is a -6 area. But then we have to do the opposite of x, or that negative number. Does that make sense there? I have a former coworker that the way that she describes it is that when we are going to the right, we're moving in the positive x direction. And here, my height is a positive. So a positive times a positive is a positive. If we are moving here to the right, we're moving the positive direction, but my height is negative. So positive times a negative is overall negative. If we were to go backwards, if I go backwards here, I'm going in the negative x direction, but my height is positive, so negative times positive would give me a negative value. And here, if I go in the negative direction, I have negative in the x direction, but then my height is negative, so negative times negative is positive. That's a way that you could also think of instead of pulling out the negative social bounds. Personally, because we don't always have the graph, I think it's easier just to switch the bounds if needed. Other questions on this whole absolute value stuff? Yes?
Just the next 21.
Is that the absolute value?
24.
Okay. So 24 says the absolute value of f of x from -6 to 6. So what that's doing is it's again going to take my entire function. I'm going to reset this up here. Okay, there's the reset. It's just. Should I even try? So it said -6 to 6, right? And I believe 1, 2, 3, 4, 5, 6. So that's essentially the whole graph. So what that does is I have this as my function, but this whole thing goes up. So I have 1, 2, 3, 4, 1, 2, 3, 4. And I still have this as my function. And then again, this, because it was negative, now becomes positive. So now I'm finding the area under each of these curves and add them together. So we should have positive plus positive plus positive plus positive. All right. Other questions with the absolute values? Okay. Now I want you to turn to your shoulder partner and tell them what's going to happen with number 23. We have absolute value of negative f of x. So turn to your shoulder partner. Make sure we're all awake. Alright, let's go and bring it back up front. We can think of this as from -2 to 1 of the absolute value of -1 times the absolute value of f of x. So you can split up that value over multiplication if you would. What's the absolute value of -1? 1. And absolute value of f of x is going to be, I think we did that earlier. Here it is. So what this ends up being is just simply from -2 to 1 of the absolute value of f of x. Okay, so I think that looks, yeah, the same as 22 to the opposite. Questions with that? So that negative didn't really have that much of an impact. Okay. So now let's take a look at these transformation ones, 28, 29, and 30. So think back to your Algebra 2 days when you first learned parent graphs. We know that general transformation format for absolute values, quadratics, cubics, linears, exponentials, you learned like a million parent graphs. And do the same thing with all your trig stuff last year. Don't forget to study trig, by the way. So if I go back to, let's just do my absolute value graph. How does h affect my graph? Good, shift left, right. So with 28, I have f of x plus 1. I can see this is grouped with my x. So that will affect my x and it'll shift to left, right. What specifically do we have happening here? Good, left 1. Alright, 29, what's happening here? Up 3. And 30, what about happening? Right 2. So it's grouped with their x, so it's going to affect my x's right 2. Okay, now for 28 through 30, we are not using the diagram above. We are using this information here. But to help us kind of visualize what's happening, I'm going to use the diagram just to help us visualize, and we'll kind of talk about what it does for us. Okay, I'm going to rewrite this over here. So that first one, 28, was from 0 to 1 of f of x plus 1 dx, which we said is just our original function shifted left. Okay, so again, we're not using this diagram, but just to help us kind of recognize what's happening. Okay, so if I were to take my graph, so originally I would be looking from 0 to 1, but not of f of x, but rather of f of x shifted left 1. So instead of finding this area here underneath the curve, rather than finding this area underneath the curve, that would have been if it was my original graph, but my graph has been shifted left 1. So watch what area we're working with instead. So I'm going to just go ahead and trace this piece. Ooh, that was pretty bad there. And it got shifted to left 1. So this is my new graph that I'd be working with. So now when I'm going from 0 to 1, I'm actually finding this area under the curve, right? My curve now is just that height. I'm finding that rectangular piece. What was from 0 to 1 has now been shifted over from -1 to 0. So if we look, this is actually the piece that had occurred just to the right, right? Because everything got shifted left. So what was here got shifted left, and that is now what I'm looking for. So what kind of happened here is now, instead of me looking at from my original, this triangle piece from 0 to 1, I'm essentially now finding that area that on the original was from 1 to 2. Now my transformation, for my transformation, there we go. Okay, it was all together. For my transformation, that was here to the left, but that's the same piece as what was to the right on my original graph. So what we have then is we were going from 0 to 1, of f of x plus 1 dx. Again, this shifted everything right, so what it changed is that this is essentially the same thing as, instead of from 0 to 1 of my original, if I'm looking back to my original, because that information they gave me down below did not tell me anything about the transformed graph, only the original. So if I bring it back to the original, notice how instead of my bounds being from 0 to 1, it's actually of my original the bounds from 1 to 2. So to make it a little bit easier rather than seeing the visualization of the graph here, if I look and see, if I take 0 and put it in, of my transformed graph, that would be the same thing as 0 plus 1 is 1, f of 1 of my original. Look, if I take 1 and put it in, that would be f of 1. If I take 1 and put it into my transformed graph, that would be the same thing as f of 2 of my original. So I take 2 and put it in. So essentially what we have happening here is my x bounds just simply got 1 added to it. And again, that's because my graph got shifted left, which means the same area that I was trying to find was 1 to the right. So really what it does is it just takes my bounds and adds that 1 to it. Then that puts us back into the running of something that they did give us. Because they did not give me anything about the transformed graph. But again, I know the same thing as if I take 0, put it in 1, 2 of my original, and I believe they did give that to us. Just like similar thing with 30. Again, the graph got shifted right to the piece that we were wanting to work with is going to change the bounds. So this would be the same thing as, if I take 2 and put it in, 2 minus 2 is 0, so it's the same thing as f of 0. 4, put it in, 4 minus 2 is 2, so same thing as f of 2. Again, in my original graph. And again, they did give us that piece, which is 2. Questions on that? Okay. Now, 29, though, it did not affect my x-values. It simply took my whole graph and shifted it up 3. This doesn't affect the bounds at which I'm looking because I'm still looking underneath the same piece of my graph. It's just now we have additional material to work with. So if this was my original graph there, and it gets shifted up 3, why did it move together before and now it won't? Something like that. Now we have the same area we had before, but in addition to it, we also have this rectangle added onto it, right? So we're going for that piece. Again, we're just using the graph to help us illustrate it. From 0 to 2. So from 0 to 2, I did have only this piece here. Well, now I have that piece as well as this rectangle underneath because it got raised up. Well, this rectangle is just simply that height of 3, and my distance here, my width is 2, or 2 minus 0. So I just simply have the same area I had before plus an additional area of that rectangle. And since it was all above the x-axis, then it ends up getting shifted just higher above it. Now, in terms of our calculus rules that we learned last class, yeah, we learned this last class. So in terms of our calculus rules we learned last class, we know that we can split up our integral across 2 functions. Since f of x and 3 are 2 different functions, f of x plus 3, 3 is outside of my function, not contained inside like it is with 28. Then I can break this up into the integral from 0 to 2 of f of x dx, plus the integral from 0 to 2 of 3 dx. And again, using those properties that we learned last class, this is just that area underneath the curve. This here, we learned was just simply your height times the difference in your bounds, which again is just the height of the rectangle and the width of the rectangle. So you add all that together. So you technically didn't need to think about the shifting up 3, you can just use your properties of it. But that's the idea that's happening. Shifting up 3 gives us this extra rectangle that we have. Okay, questions on that? Okay, I want you to now stand up, turn around, and sit back down because half of you are falling asleep and you can't have that. I want to see every single one of you stand up, turn around, if it's necessary. Beef, I need to see you stand up. Ever you can stand up. I stopped you, did you stand up? Since I told you to stand up? Do a complete 360, not a 180. Okay. Have a seat if you have not sat back down yet. We're going to take a look at 31, and we have a little bit of notes that go with this, so you can throw it wherever you want. It's just going to take 1 page. It's really reviewing what's even and odd, but what I've learned is some of us have forgotten. Here's this right there, too full of stuff up there. What's that? Yes. I'm not in it. Alright, 31 says, what is my integral when my function is even, and what is our integral when the function is odd? So, real quick, turn next to your shoulder partner and explain what is an even function, what is an odd function.
Same way, opposite way.
There's some logical reasons.
In my face. I just have a lot of
Alright, go and bring it back up front.
mouth open.
Who can explain to me what an even function is? Is that a hand raised out? What is an even function? You've got a couple different ways you can explain it. This is how they express this. Ooh, very close. We don't want x-axis, we instead want the y-axis. So an even function is a function that is symmetric across the y-axis. No, that looks right. Does it cross the whole thing? It was right the first time? That one looks weird too, but I trust you guys. Okay, across the y-axis. So symmetric across the y-axis, that means if we fold it in half down the y-axis, we get the same thing on both sides. Who can think of an example for I saw it, I love it. You give me the function words. Good, x squared. Absolute value is also true. Alright, so our example is f of x equals x squared. If we fold this in half down my y-axis, we have the same piece on either side. Now, algebraically speaking, and this is what your teachers, I'm sure, made you do. If I take negative x and put it into my function, so I'm just going to go and test this here. What is negative x quantity squared? Positive x squared. So what we do is, when we take negative x and put it in, we end up getting back the exact same function. So even though we put in negative x, we get back the same function. Alright, now let's take a look at odd. What does it mean for a function to be odd? Symmetric across the origin. What does that mean to be symmetric across the origin?
If you flip it upside down,
Well, not just upside down, but also like that. So 180-degree rotation, or what I think is a little bit easier to think of is flipped both x-axis and y-axis. You can think of a pretty simple example for this one. X cubed. X is also true, but x cubed is a little more exciting. Alright, so let's take a look at x cubed. Pretend that went through my origin. Oh, looky there, it does. Okay, so again, if I were to take this piece here. Max, are you writing this down? Alright, so if I were to take this, flip it upside down and across, I get that other piece of my function. So symmetric across the origin. Now what this looks like for us algebraically is if I were to take negative x and put it in, quantity cubed, what does this equal? Good, negative x cubed. So when I take it, negative x put in, I get back the opposite of the function. So odd gives you back the opposite, even gives back the same. Now, where this comes in handy for us in calculus is dealing with area underneath the curve. So let's say, for example, I just went from -2 to 2 and found my area underneath the curve. Assuming that I drew this properly, what can you tell me about my area underneath the curve? It's the same on both sides, right? So we could rewrite this as, and I'm just going to do a generic method here. So negative a to a of my function. If it is an even function, this is same as just twice the area from 0 to a, or the area from negative a to 0 of my function. So if I know a function is even and I know this piece, I can know the area for the whole piece there. Now, for our odd function, what do we notice about our area in these? Equal and opposite. So it's the same amount but opposite sides. So, let me bring that up. Again, I could rewrite this as the area under the curve from negative a to a of my function. If it is an odd function, would simply be what? 0. Okay, so again, if I know my function's odd, and it's symmetric about that origin, and we're going from the same bound on the left side and the right side, then we know it cancels out. Now, this is more commonly seen with trig functions. Don't forget to study trig. Real quick, let me go ahead and pull up another page. Actually, we'll just go some pages. Alright, my sign graph, is that going to be even, odd, or neither? Odd. Odd. If I take this piece, flip it upside down and across, we get that same piece there. So this is an odd function, which that's important to know, that if I have sine of negative x, odd gives me back the opposite, right? That is the same thing as negative sine of x. Bear that in mind. All right, and then cosine. We can start there. What type of function do we have here? Even. It's the same on either side of my y-axis. So this is an even function. So again, important to keep in mind is that cosine of negative x is just cosine of x. Okay. So we can use these properties to help us more quickly evaluate those integrals. It's not super duper common that we use this, but you might see multiple choice sneak up in this regard. Okay, so then looking back at that problem on the homework. If our function is -1 from 0 to 3, find the integral from -3 to 3 if it's even. So what would my answer be if the function was even? -2, good, it's just double that. And what would it be for odd? Okay, questions on that? Perfect. Alright, you should be getting 3-3.
I have.
Is there anyone that did not get 3-3?
Because negative numbers that are positive, that's what number is equal to delta. Equal to delta.
Alright. In some space, wherever you want, I want you to do the following integrals. Not integrals, sorry. Alright, I'm going to give you 3. Let's just actually go with 2 derivatives. And I want you to find the function that will give me those derivatives. Alright, so I've given you 2 derivatives. I want you to find the original functions that will yield those derivatives. Feel free to try on your own, work with someone nearby you. And if you know this from physics, don't spoil the fun for others.
So you gotta do the opposite derivative. That's easy. So x is x squared, and then that bottom.
On the second one. Right.
Originally it was one times, so it would be like 4 times 4.
All right.
Long. I like to
That does make sense. That's 1/4 so then 4. Because when you bring down 4, it's 4, and you get and then be plus 2.
Alright, raise your hand if you think you know the first one. Raise your hand if you think you know the second one. Alright, let's see how we did. So again, we're trying to find the function that will yield this derivative. What do we get for our first function? Stephen?
It's x squared plus c.
X squared plus c. Ooh, what is that? C. A constant? What constant do you want? Any constant? So raise your hand if you had just y equals x squared. Raise your hand if you had y equals x squared plus some number. Okay. So the reason why Stephen put in that plus c is because we know that just y equals x squared will yield this derivative. But so will y equals x squared minus, I don't know, 8, 87, 187. All of those will yield still that same derivative. Why? Good. The derivative of a constant is 0. So no matter what our constant is here, whether it's positive or negative, it ends up going away within our derivative. So to kind of give us a generic solution, we do plus c. This c just simply represents some constant. We don't really know what it is, but it could be anything. So it's infinite solutions here. So this is what we call the general solution, where it just gives a generic c for whatever constant we need. All right. Who would like to give the second one a try? Nick?
X x4 over 4 plus 2x.
X to the fourth over 4 plus 2x. Raise your hand if you agree with this. Okay? Alright, so if we take the derivative here, I have to bring down my 4, reduce the power by 1. Here I have to, now this x ends up going away, so I have my 4 is reduced and I have x cubed plus 2. So that would work. But again, we have the same situation. I could have any constant tacked onto the end here. Right now we just did a constant of 0, but I could have any constant tacked onto the end and still yield that same derivative. So notice what we did here. We know that our power has to increase by 1 in order to go back a step, right? Because when we take a derivative, we decrease the power. So we know that we have to increase the power by 1. But why? Where did this 1/4 come from, or the being divided by 4? Why is that there?
Because when you
Let's go with isometry. If your answer was good, let's go with isometry then for another group.
Because you would just take the derivative of x to the fourth would be 4x cubed. So you're going to have to get rid of the 4 exponent and get 1. So it has to be 1/4.
Beautiful. That was an awesome explanation. So, yeah. Alright. So if we had just x to the fourth, then again, as isometry said, we have to bring down that 4 and multiply in front. But we do not have a coefficient where we have a coefficient of 1. So to counteract it, if you would, we have to divide by 4 so that that would give me that coefficient. Very good. Alright, so taking a look at our actual notes, you can see it says antiderivatives of polynomials and indefinite integrals. Well, an antiderivative is simply that function that when I take the derivative gives me what we just had. So what we were just doing, these guys here, that's an antiderivative for this. And this here is an antiderivative for this function here. It's again, if you would, that previous function that when we take the derivative of it yields this here. Yes?
Are integrals antiderivatives or is
We use integrals to get the antiderivative. So our answer is the antiderivative. So let's go ahead and combine this together. Let's take a look at that. So that's what we have here. The integral of f of x dx equals f of x means that if I were to take the derivative of my result, I should get this original function. So this f of x, this is my antiderivative. This is the function that when I take the derivative of it, gives me that inside function. Now notice it also says indefinite integrals. We've been working with just definite integrals so far. What do we notice the difference is with each of these compared to what we were working with before? They have a function. What else? There are no bounds. Very good. So indefinite integrals is where we have no bounds. And thus they give us that antiderivative, that function beforehand, that if we take the derivative gives us the inside. A definite integral gives us a limitation, a starting point and a stopping point to which we find that area. So whenever we have the indefinite integral, we should always have that plus c. Now that is extremely important. If you give me an answer without plus c, it is wrong. If you have multiple steps and plus c only appears in one of those steps, it is wrong. It needs to be in every single step. The second that you take that integral, the second that you find the antiderivative, you need to have a plus c all along the way. Okay, so it's extremely important. Now here at the top of our notes, it's simply just comparing our differentiation rules with our integration rules. And we, last class, covered almost all these integration rules. So we'll just go through this pretty quickly. The integral of 0 is a constant, which makes sense because the derivative of the constant is 0. The integral of some constant is just that constant times x. And notice we have that plus c on the end. And again, this makes sense because this is essentially kx is 0 dx. All right, I hear a lot of chattering, and there should not be talking. This second integration rule is essentially x to the 0th power, right? Because what is x to the 0th power? Just 1, which would give us 1 times k is that. So if I were to go to the rule before, I would need to have an exponent of 1, as we can see here. And we don't have to worry about the fact that bringing down that power would mess with my coefficient, because 1 times anything is just that. So if I have just a quick example, integral of 5 dx, that would simply be 5x plus c. Alright, this next rule is just our coefficient can come out in front of our integral. Just like our derivative, we said we could, the derivative of a coefficient times a function, same thing as the coefficient times the derivative of the function, so that coefficient can be brought out. Same thing with our integral, we can just simply take this coefficient and bring it out in front. Alright, and then we have sum and difference. So if I have an integral of 2 functions added together, it's the integral of each individual function added together. Same with subtraction. Just like our derivative, we can break that up over plus or minus 1. Alright, now this last piece, this is our biggie for today. Alright, so this is kind of the biggest rule for polynomial integration. Integrating polynomials really isn't that exciting. It's more fun to integrate trig functions and natural log and exponentials. They all have their own individual rules, but for a polynomial function, this is the main rule that we deal with. And this is essentially the power rule reversed. So we learned that from our beginning pieces. We know we have to increase our power by 1, because when we do the derivative, we would normally reduce the power by 1. So to go backwards, we need to add that back in. So we increase the power by 1. And then we have to divide by that new power. So that's this piece here. New power. That will help us counteract that the power rule, we bring our power down, multiply by it. So we have to divide by our new power to help counteract that. And then always have that plus c on the end. Alright, so let's just real quick go ahead and do example 2. We have the integral of x to the 5th dx. So again, we increase the power by 1, so x to the 6th. Divide by my new power, and then just plus c on the end. And that is my answer. So again, I increase my power by 1, divide by my new power, and then we have plus c on the end. Because it's an indefinite integral, you need to have that plus c. We do not have a plus c for definite integrals, only for indefinite. Alright, go ahead and give number 3 a try. Do we agree with this answer here? So we have our power increases by 1, so it's x to the 13th. Divide by your new power, which is the same thing as multiplying by that 1 over 13. So you can write it like this or like that. Either way is fine. One's not necessarily preferable over another. Depending on your coefficients you're working with, one might be desirable. That's all there is to it. Alright, now with number 4, we have that sum and difference rule happening. So technically what this is the integral of x to the 4th dx minus the integral of x squared dx. Notice that each piece, if I have an integral, must have that differential with it, the dx with it. I cannot have integral of a function without that differential specified. It will be wrong. You must have proper notation here. Alright, so let's go ahead and integrate x to the 4th. So again, I increase my power by 1 and divide by my new power. And technically we have a coefficient, a constant that goes with that. I'm going to call it c sub 1. And then for this piece I have a minus. So again, integral of x squared, I increase my power by 1, divide by my new power, and that has a constant. Now, you'll notice that the sum and difference rule here just simply has one big old constant slapped onto the end. And this is why. What is a constant plus a constant? It's just some constant. What's a constant plus a negative constant? A different constant. Might be positive, might be negative, might be 0, 0 is still a constant. So it's not really necessary for us to write each individual constant. We would go ahead and just simply write x to the 5th over 5 plus x. And nope, minus, it's minus there. X cubed over 3 plus a big old c. So it's not necessary for you to write the individual constants, just tack one on at the end. If you wrote c sub 3, that's perfectly fine. It still represents a constant. But we'll just write plus. Also, this is using my sum and difference rule, but I trust that you guys can handle breaking that up into your head. So really, if you had, for step 4, you went from the given straight to this answer here, that would be perfectly fine. Because I trust that you guys can handle thinking, okay, integrate this and integrate that. Put your answer there. 1 plus c. So this would be the answer. Questions with 4? Okay. So let's take a look at when we start to have coefficients. So like number 6. So we have the integral of 10x to the 4th minus 2x squared. Alright, so again, we know we're going to break it up over that. So let's just go and do the integral of the first piece. So that 10 is just a coefficient that gets to hang out with it. So I have 10x to the, my new power is 5. And I have to divide by my new power of 5. Alright, then I have minus 2x, my new power is 3, divided by that new power of 3, plus c. Now if this is for response, you can stop there and you're done. But we could simplify more and reduce this to be 2x to the 5th minus 2/3 x cubed plus c. Either way would be fine. Questions with that?
Are there problems that will also give us the integral and ask us to go back to find the integral we did earlier?
It could. And we'll have a problem that's similar to that on the back side of the sheet. We'll have something that's similar to it. Where if they ask you to go back, you would need to know that means integrate histories.
Can you skip the middle step and just go to 2x? Okay.
Yep. I trust that you guys can divide in your head as well.
If I put 2x third over 3, is that okay?
Yeah, you can have it either like this or like this. Either way is fine. Now you guys have to be careful when we get to problems such as, let's go with number 8. They start off giving you fraction coefficients. Alright, so it's still the same thing, just take it a piece at a time and be careful as you work through. Some of us struggle with arithmetic.
Especially if you're on time crunch.
Especially what? If you're in a time crunch. So remember, for response, you don't have to simplify unless there's trig or complex fractions. We do have to take care of those. But otherwise, you don't simplify. And please don't, because some of you guys are losing easy points because you simplify wrong.
Unless trig or
Trig and complex fractions we have to do. Alright, so again, 3/4 is that coefficient hanging out. So my new exponent is x to the 6th divided by 6 plus 5/3 x cubed divided by 3 minus, and again you could write that as 1/2 x or x over 2. My new exponent, I'm going to write as 1/2 because I think that might be specific. So 1/2. My new exponent is x squared divided by 2 plus c. We are multiplying each of these, and you could stop right there for free response. Of course, we could simplify as well. Questions with that? Okay. Go ahead and do 9 real quick. Why not do one with pi? We should have our answer. Should be that. You guys know you wish you took stack, right? Hey, listen. Well, who is that that's insane? Hey, listen to Kitty. Okay, don't say, oh my goodness, I don't know anything about this. It's okay. They listen to Katie. Okay, did we get pi x squared divided by 2 plus 1 over pi x plus c? Or x over pi plus c? So is pi a variable? No, pi is just a constant. So this is just my constant. I increase my power by 1 divided by my new power. This is just a constant. So think of it as 2. If it was plus 2, you do 2x. So you just do 1 over 5x. So pi is just a constant. Yes, yes. Alright, other questions with 9? Okay, real quick, let's take a look at 10 and 11. How can we rewrite this so it's easier to work with? X to the negative second, yes. It's still going to be the same process, just be careful as you add and divide. Okay, go ahead and flip it to the back side. Let's take a look at 13. Now, we were not given an integration technique for radicals, only power rule. So how can I rewrite this? 2y to the 1/3 minus 4y to the 1/4.
How much is the dy though?
dy. Now we can just apply our rules like we were doing before. And again, be very careful. These are fractions. I know we all start to sweat a little bit when we see fractions. It evokes the same fear trig does in some people. Alright, so again, my coefficients just hanging along for the right. What's my new exponent here? 4/3. And I divide by my new exponent. Come on. You can do it, smart. Alright. And then minus 4y. What's my new exponent here? 5/4. Divide by your new exponent. Plus c. Now, can I leave my answer there? No, it's complex fractions. But don't go crazy simplifying. If I'm dividing by a fraction, isn't that the same thing as just multiply by the reciprocal?
Yeah.
So 3/4 times 2y to the 4/3. You just took care of your complex fraction issue. Minus 4/5 times 4y to the 5/4 plus c. Multiply if you really want, but please don't mess it up. So with that being said, as you start to get the hang of it, when you go through and do the problem, you might be able to just go ahead, like when I would do this problem, I would go ahead and write, alright, 2y to the 4/3, and then I would multiply that by the reciprocal and combine it all together. Kind of cutting out that number. But again, as you get more comfortable, you can do that. But just be careful with all those fractions. Remember, we cannot have complex fractions. Alright, questions on that? Okay. So we'll wrap it up with, I think it's number 19. Real quick, be careful though, 16, 17, 18, they tell you a trick to use here. We don't have product rule, chain rule, quotient rule with integration. So you would need to first multiply this out. Here we can reduce each of those terms and then integrate. Okay, so just like we do with our differentiation techniques, you can use that formula. Okay, the more exciting piece. 19, 20, 21, and 22. So it says differential equations, solve the differential equation. Differential equation, the reason it's called that is because it's an equation with a derivative, differential derivative. And notice it says, i.e. initial value problems. That means that we are going to find our actual C, that actual constant. What they've done is they've given us enough information to actually solve for what my constant is and find the specific solution where we have that constant filled in, rather than the generic solution where it says plus C. Alright, so when it says solve the differential equation, what it means is find what your original function f of x is. So here for 19, they give us our first derivative is 3x minus 1. Well, f of x is just simply the antiderivative of my derivative. Or if you would, the integral of my derivative. Remember, integration and differentiation, integrals and derivatives, are inverse operations that cancel each other out. So if I integrate my derivative, that gets me back to my ratio, which is what we were doing in the beginning. Okay. Well, they gave us our derivative, so the integral of 3x minus 1. And what does that give me, the integral of 3x minus 1? 3 halves x squared minus x minus c plus c. Good. So we still have to write that plus c because it is an indefinite integral. But now we have a function for f of x, just we don't have that constant. But lo and behold, they gave us a point that our function passes through.
Wait, so for that one, it's an f of x or f prime of x?
This is f of x. I'm integrating f prime of x, which gives me my original. Okay, so they told me, hey, this function passes through the point 2, 3. So my y value is 3. My x value is 2, so I'm just going to substitute that in. And we can solve for our c. Let's see, so we get 3 equals 4, 12 divided by 2 is 6. Minus 2 plus c. 3 equals 4 plus c, so c is negative 1. Do you agree with me there? Okay, so that tells me, hey, I know the specific solution, the specific equation. So my final answer would be f of x is not just this generic one, it has to pass through that point, and we solve through that c value. So we have 3x squared over 2 minus x minus 1. That would be your answer. It's kind of like back in Algebra 1, you know, eons ago for you guys back in middle school. Remember how when you had y equals mx plus b, and if you had the point, and you had slope with something, you would take those values, you'd put them in, and then you would solve for your y-intercept and put it back together, right? The same idea here. Oh, come on, guys, I did with the geometry kid just the other day. When they would ask you to write the equation line that passes through this point with this slope here, so we would take each of those values, put it in, and solve for that y-intercept. That's kind of what we're doing here. I mean, that is actually our y-intercept for this problem. So we're essentially finding that specific y-intercept that guarantees it goes through. And what's cool with this is we can actually, with any of these, we can know we did it right. Take your derivative. Bring down your 2, we end up with 3x minus 1. Boom, that's what our derivative is. Alright, questions with that? Okay, so 21. What's different about 21 as opposed to 19? We're not doing the equation for f prime, but rather for f double prime. So we still want to find f of x, and we know to find f of x we have to integrate our first derivative, but I don't have my first derivative, so we have to find the first derivative. So my first derivative is simply integrating your second derivative. Again, integration takes you back that one step. So if I have f double prime, going back takes me to f prime. And they were so nice to give us a really easy second derivative. Make sure you're writing the dx on the end. What is the antiderivative of 2? Get 2x plus c. So that's my first derivative. But again, we don't know what that constant is, but oh, looky there. They gave us an initial condition that we can find that constant with. So again, my y value is 1. My x value is 4. Solve for c, 8, subtract it over, -7. So my first derivative, the actual specific solution, would be 2x minus 7. Yippee-tie-yay, but we're only halfway there. These are the exclamations you guys use in your head, right? Okay. All right, are we good so far?
No.
Questions on this? We're not done yet, Nick. We're just halfway. Questions on what we've done so far? Okay. So now we need to actually find my original function. And we know our the original function is simply integrating my derivative. Don't lose your dx. But now we actually know what our derivative is to integrate. So the integral of the derivative we just got, 2x minus 7 dx.
Good afternoon, Herndon. In conjunction with National Kids at Hope Week, this week we are celebrating We Are Herndon at Herndon High. Help us celebrate Herndon by showing up your school spirit tomorrow and wear a red block. Go Herndon, have a great afternoon.
Okay, so when we integrate plus c, technically this is a different constant, so it makes me wary using c for both of them. You can call it d, you can call it c sub 1, call it m for Margaret after math. But that's just a technicality. It's nothing to lose sleep over. Okay. Again, we have our initial condition. So my y value is 2. My x value is -1. Solve here. We get 2 equals 1 plus 7. Let's see, that's 8. Subtract it over. -6 equals 1. So finally I can say my original function, the specific solution that will pass through this point, give me those derivatives, is x squared minus 7x minus 6.
How'd you get x squared minus 9x plus 7?
Great question. So if I take this piece, 2x squared divided by 2, 2 3's. So your homework is to finish this worksheet 3-3. Notice we do have a quiz next class over the first 3 lessons. So make sure you are checking the key on Blackboard. Come prepared with questions right away.
What did you tell us that we needed to do trig for? Like, remember, at the
In December, we're going to have a trig unit. So make sure you're studying trig. Have a good day.
Can I ask questions about my basically before my next one?
Yeah, I'm after school nearly every day.
Okay.
30 before 7:30. Have a good day.